Okay, thank you. Welcome to the STC training ocean forecast system. We will discuss coastal hydrodynamic model. I would like to introduce myself. My name is Bayu De Pratama, and I will accompany by Widya Iduntias to try to explain about the coastal hydrodynamic model. And this is the online presentation for this session. The first one is we talk about what is the background for this model, and the second one is what definition of the hydrodynamic model, and the third one is how the hydrodynamic model works. And next, we will try to explain about the type of hydrodynamic model. And the next one is the simulation, the hydrodynamics model. We will use Delft 3D model developed by DataRes. And the last one is we try to explain about the example of hydrodynamics model in Indonesia. And as we know, the ocean process are nonlinear and turbulent, and the theory of nonlinear and turbulent flow in complex basin is not well developed right now. So that's why for understanding the ocean, we need some parts like a data, numerical model, and theory. And the theory will be used for describing the ocean, a much simplified approximation to reality. And the second one, we also need the observation, the data. As we know, the ocean observation around the world is still sparse in the time and also in the space. Actually, the data will provide a rough description of the time average flow, but the many processes in many regions are poorly observed right now. And the last part is the numerical model. The numerical model will include a much more realistic theoretical idea, and the numerical model can help interpolate the oceanic observation in time and space, and the numerical model also will be used to forecast the climate change, the current, and wave as well. So by combining the theory, the observation, and the numerical model, we will avoid some of difficulties associated with its approach used correctly. So with those components, we will get the deep understanding the ocean, and then we can use for the prediction of the ocean. And the next slide is why the ocean modeling is important. As we know, the operational marine monitoring and forecast system has been transformed the marine observation into the analysis and forecast products of marine condition, thereby enhancing the information value of the observation systems. And overall schematic design of such a system which display information flow for an operational marine monitoring and forecast system, illustrating the basic components developing products from marine analysis and forecast to end users. And circulation modeling represents one of the main goals of operational marine monitoring and forecast system. It provides an overall description of ocean physical essential variables like temperature, salinity, current, sea surface height, ocean heat flux, and etc. for ocean prediction and for supporting the climate studies. The ocean models are able to describe the sea state from the global to coastal scales and to predict its variability and evolution in time from short to mid-term or to long-term, This is done by numerically solving a set of partial differential equations based on approximated version such as governing equation are part of the theoretical fluid dynamics theory and the historical tradition in the contributions of several governing equations. And to improve the quality of predictions, the data assimilation techniques and also the ensemble techniques are widely used, and their primary scope is to rigorously and systematically combine available observations in situ or satellite or remote sensing data and numerical ocean model to provide the best estimate of the forecasting cycle. Observations are also used to provide the quantity of understanding of the scale of the ocean model by means of validation and calibration techniques, and consequently to measure and monitor the accuracy of the forecasting products. And actually, we can divide the numerical model in oceanography into two classes. The first one is mechanistic model, which is our simplified model used for studying process. And the second one is simulation model, are used for calculating realistic circulation of oceanic. And the first simulation model were developed by Craig Bryan and Michael Cox at the Geophysical Fluid Dynamics Laboratory in Princeton. Their model calculated the three-dimensional flow in the ocean using the continuity and momentum equation with the hydrostatic and bosonic approximation and a simplified equation of state. And there are several types of the ocean model. The first one is the wave model. We know the sum model to the wave simulation, like a WaveWatch 3, Swan, WAM from Europe Companion. And the second one is the ocean circulation, which is include coastal hydrodynamic model as well. And the next one is the sea level model, biogeochemistry model, sea ice model, and etc. In this session, we will more deeply discuss regarding to the coastal hydrodynamic model. So before we continue the next session, I would like to give the one quote from Tony Thomas. He said models are providing insight, not the answers. So what is the hydrodynamic model? Hydrodynamic model is the study of fluids in motion, or we call the fluid dynamics. This model are an efficient and comprehensive approach to representing the coastal water dynamics. And this modeling forms the basis for many modeling studies, whether sediment transport, morphology, waves, water quality, and or ecological changes are being investigated, included carried out to improve the representation of tides, waves, currents, and surge in the coastal water. So what is the coastal hydrodynamics has been mainly concerned with extreme storm surge, tide and wave prediction for flooding, tidal flows for navigation, the coastal protection from wave action, the coastal erosion, port and harbor design, the outfall design, around structure, and also the large-scale morphodynamics on the continental shelf. So there are several uh, zone in the coastal hydrodynamic, we must know the coastal zone is situated between the coastline and the shelf is the territory of winds, wave, and currents. Usually, the coastal zone is subdivided in three zones. The first one is beach zone, this zone is dominated by wind and wave forces, and the second one is soft zone, which is this zone is dominated by breaking wave and wave-induced currents under calm conditions. And the soft zone may be reduced to a narrow swath zone, but under storm it may extend offshore to depths of 10 to 8 meters, 8 to 10 meters, where the wave first begin to break. And the last one is the middle and lower surface, which is this zone dominated by non-breaking wave and tide density and also the wind induced current. So what is the hydrodynamic process in the coastal zone? There are several processes in the coastal zones. The first one is wind-induced wave. This is the most important factors that can control the growth of the wave, or the wind speed, the wind duration, and how long the wind blows, and also the phase. And the second one is tide-induced current. Tidal currents occur in conjunction with the rise and fall of the tide. The vertical motion of the tides near the shore causes the water to move horizontally, creating currents. When a tidal current moves toward the land and away from the sea, it will be called the floats. And when it moves toward the sea, away from the land, it we call ebbs. And tidal currents are controlled by several factors like pressure gradients, the bottom friction, and also the Coriolis force. And the hydrodynamic process, the next hydrodynamic process in the coastal zone is the wind-induced currents. There's two types of wind-induced current can be distinguished. The first one is wind drift currents of relatively short duration generated by local storm winds. And the second one is large-scale circulation system generated by long duration effects of such as trade winds, zonal wind, and atmospheric pressure system like Gulf Stream, Florida current, and the equatorial current as well. And the next hydrodynamic process in the coastal zone, the density induced current, which is the density variation will be induced by salinity variation, are most commonly the result of river from the fresh water of relatively low density, and in the coastal zone where the fluid density is relatively large. This will lead to horizontal and vertical circulations. And density induced current are related to spatial density gradients of the fluid sediment mixture due to variations of temperature, salinity, and or sediment concentration. And density variation induced by temperature effects usually are related to a surface layer consisting of relatively low density, which is or warmer water, and a bottom layer of relatively high density cold water. So we can divide the oceanographic model to the baroclinic model and barotropic model, which is the baroclinic model is the component of flow driven calculated from the slope of the internal density, and the second one is barotropic component model, which is the component of flow driven calculated from the slope of the sea surface. And the next one, what is the hydrodynamics process in the coastal zone, is the wave-induced current. the refraction of the waves by the horizontal currents. So we know the refraction of wave involves a change in the direction of wave as they pass from the one medium to another medium, and reflection also, or the bending of the out of the waves, is accompanied by change in speed and wavelengths of the wave as well. And generation of longshore currents also can be generated by breaking wave. The longshore currents are affected by the velocity and angle of a wave. When a wave breaks at the more acute or steep angle on a beach, encounter a steeper beach slope, or is very high, longshore currents increase in the velocity. So we will next to the agenda regarding to the how the hydrodynamic modeling works. And numerical modeling consists of solving the hydrodynamic equations directly in the tidal wave propagation zone. In theory, it is used to calculate the tide at any point in the zone. It involves dividing the zone into elements of simple geometry called the grid cells and applying the following principles. The first one is the principle of conservation and the principle of dynamic, which is the definition of flow velocity in grid cell depends on external forces acting on the column of water contained in the cell. There are three types of forces, like cross pressure forces due to difference in water level in the surrounding grid cells, and also the Coriolis force due to the rotation of the Earth, and the braking force similar to friction, which is exerted near the bottom and sides of the grid cells. And what is the characteristic of the coastal hydrodynamic model? In practice, the grid cells are square, rectangular, or triangle finite elements. The choice of the cell size is key. The smaller they are, the better the accuracy. However, the smaller the cells, the more cells there are for a given area. Moreover, the time step is not independent on the grid cell size. Too large a time step can generate numerical instability. As a result, a smaller grid size significantly increases the computation time, and the cell size is therefore chosen so that computation time remains reasonable. And another major limitation is the knowledge of depths. It is pointless to try to refine the resolution of a model if the environment is not described at an equivalent level. From this point of view, nautical charts cannot provide suitable bathymetric data for hydrodynamic modeling because they are generated by soundings whose primary function is to identify elements affecting the safety of navigation. Information density is often sacrificed to the enhanced chart readability and the terrain that may pose a danger, like which can distort the objective representation of the seabed. So that's why we need to transition from two-dimensional to three-dimensional results in better predictions, better accuracy of result due to the better spatial resolution near the coast and at harbor accesses. And the second one is better consideration of important processes like bathymetry, bottom friction, turbulence, and also the better standing of the area studied, more in situ measurement. And the fourth one is the better the presentation of shear and improve the performance of telemet code since the late 90s. And this agenda, we will try to explain some of kind the hydrodynamic model like ARCIC, CMS flow, Delft 3D, and etc. And the first one is the ARCIC. ARCIC is the coastal circulation model, which is have the spatial dimension in 2-dimensional and 3-dimensional spatial dimensions. And the model domain is the coastal domain, and online one line the model description is coastal circulation and storm surge model. And ASIC is system of computer programs for solving time-dependent free surface circulation and transport problems in 2 and 3 dimensions. And the ASIC application typically have included the modeling tides and wind-driven circulation, and also the analysis of hurricane storm source and flooding, and dredging feasibility and material disposal studies, larval transport studies, and nearshore marine operation. And the second one is Delft 3D model. The 3D model have the 2-dimension and 3-dimension spatial dimensions, and this model is the hydrodynamic and sediment transport model, and this model can use for wave current interaction, non-hydrostatic flow, to simulate the salinity, the temperature, and the water quality, ecology, and etc. And there are several processes represented by the model, like the drying or flooding, turbulence and large eddies, and stratification, the internal wave, and density of salinity, temperature and sediment, and etc. And what is the physical parameter and equation in this model? There are water level, the velocity, the temperature, salinity, density, and several physical process in biology process as well. And Delft 3D model, the hydrodynamic model is based on the full Navier-Stokes equation with the shallow water approximation applied. And this model also can install and running in our PC desktop with the minimum processor 1 gigahertz and internal memory 1024 megabyte and swap space twice internal memory, and the storage hard disk like minimal 10 gigabyte. And the basic process covered by each of the model are in the Delft 3D. We have Delft 3D flow, which is for simulation the 2-dimensional and 3-dimension hydrodynamics, salinity, temperature, transport, and online sediment transport on morphology. And the second one is Delft 3D wave, to simulate the shortwave propagation, which is based on the SWAN model, and also the D water quality, Delft sediment, Delft ecology, and particle tracking or OSPIL modeling. Overall functionality Delft 3D, there are several processes like flows due to tide, wind, density gradients, and advection and dispersion of constituents, salinity, temperature, other constituent, sediment transport, morphodynamics, wave induced current structure, and online coping to wave, to water quality, to ecology, and the particle tracking as well. There are several functionality in the Delft 3D. There are two horizontal coordinate system, which is the Cartesian or matrix and spherical, and also have two vertical systems, which is surface and bottom following sigma layers and fixed horizontal Z layers. And the solver process, which is the tide generating force and simulation of dyeing and flooding, density gradient to non-uniform, and also have the four turbulence model for vertical mixing, constant, algebraic, and etc. And also have subgrid scale horizontal large eddy simulation, and have space varying wind and pressure on the flow grid or on a meteor grid, and also process the rainfall and evaporation and thermal discharge, and also heat flux through the surface. And now we will try to explain a little bit about the implementation of hydrodynamic model in Indonesia, which is we call the INACHIEVS model. This system is started on earlier 2017 based on delta-d flow and wave, which is we have some component like atmospheric forcing, the tidal component, and also the rainfall for the calculate the river discharge. And for the atmospheric model and the atmospheric forcing, we use it will be used for the waves model in the system, which is the wave force 3 and SWAN, and also the atmospheric forcing and tidal component will be used for the hydrodynamics model, and the rainfall or river discharge will be used for calculated the river discharge using the hydrology model, which is SOBEC. And then from this system, we also do the coupling model, wave and hydrodynamics model. From the coupling model, we get the better result for the water level, for the wave, and also for water level. And from those model, coupling and hydrology model will be integrated in the fuse model to calculate the inundation or flooding on the coastal. And we calculate this system, this model on our high performance computing. We dedicated with the 520 core processing to implement this system, and we can use the MPI running and also optimization computing time and automation model run. And this is the configuration of hydrodynamics model in Indonesia. In the top one is the atmospheric forcing. We use the sum of global atmospheric forcing like from GFS and also from the SCMWF. And we also running the WAF model for the regional, our model. And the second layer is the waves model. In Indonesia, we have the BMKG ocean forecast system, which is include the wave model. In the wave model, we have the wave force 3 model using the forcing from global model, GFS and SCMWF. And then the wave force 3 model for the Indonesian region will be nested to our local model domain, which is using the SWAN model. And in the level, and then in this third layer, we have the hydrodynamic model, which is we use Delft 3D model, and from the wave model and hydrodynamic model, we do the coupled wave hydrodynamic model, and the coupled wave hydrodynamic model also have been forced by local tide station, and then output from coupled wave hydrodynamic model we send to the fuse, which is the flood early warning system in Indonesia, and the output from the coupled wave hydrodynamic model will be using for calculated the flooding or inundation in the Indonesian seas to calculate the Indonesian map. And this system we also have the nested model. As we know, the deep ocean and the coastal system are deeply connected. This means that to solve one, you need to solve the other. For example, waves in the shoreline depend on the fate at a region thousands of kilometers away. In theory, we could model the world system at once, but solving the global ocean at the resolution needed by the coastal application is computationally challenging, right? And the traditional approach to solve this difficulty is to use the so-called nesting technique to employ different model with different resolution for coastal and deep seas. So we need first a larger scale model with a coarser resolution to provide what we call the boundary conditions. And boundary conditions are the way we have to provide the coastal model with the physical information of what is happening in the outer regions. So in this system, we have 3 domains. The first one is the large scale model, South China Sea model, and we nesting to the Pantura model. The output from this model is water level will be used for boundary condition in the Pantura model. In the Pantura model, we do the couple flow and wave, which is the boundary condition from wave model. Is coming from the BMKG wave model, and then from the Pantura model we nesting to Jakarta and Semarang for the better resolution in the Jakarta Bay and Semarang Bay. And this the several parameterization in our system. The South China Sea parameterization in the large scale model, we have the wind and pressure forcing from SLWF and flow run and boundary condition time series and initial condition restart file from previous result with the time step of 5 minutes. And the second domain, Java Sea or Pantura domain, we use the wind and pressure from SLWF, the boundary condition, nesting from the South China Sea model, and initial condition is restart file from previous result. And we do the couple flow and wave model and the boundary wave model of SWAN coming from the MKG ocean forecast system, which is the spectrum wave. And the last domain is Jakarta and Semarang. The parameterization is include the wind and pressure from SWF as well, and boundary condition nesting from Java Sea model. And in this domain, we also use the updated bathymetry from our agency, the Indonesia Agency for Geospatial. And for the digital elevation for the flooding model, for the flood model, we use them from Jakarta Flood Early Warning System. and inundation calculation from the fuse model integration with the hydrologic model. This sum result and validation of the water level. The blue one is the model result, and the red line is the observation coming from our tide station in the Jakarta Bay. In this result, we get the information, good correlation between the observation and model with the bias 0.03 and error 0.09. There are for result and validation of the water level. We have the high resolution and couple model for water level, the surface current, wave height, and inundation is forecast up to 5 days. And from this output model, we can calculate the inundation warning for the coastal community. And that's all. Thank you very much. And hopefully looking forward to discuss more deeply with all of you in our synchronous session. Thank you very much.